All right, so this is the lesson for Chapter 3, Objective 3, and you can also find, so this is student guided notes, so they're kind of pre-printed, so I'll be sure to load a PDF of this if you'd rather go that route, that you could print it out, or at this point, perhaps you would hit pause and add these definitions into your notes while, or before I start going over them, okay? So the most that we're going to be what we're going to be covering for this objective is how to decide if our functions are increasing and decreasing, which is something that you are experienced with from your Math 3 days. So, but a couple of things that we need to review is our calculus definition for increasing and decreasing. So first, if we have a function, it is going to be continuous on the closed interval and differentiable on the open interval. So just a reminder, if something is continuous, then we are looking at the domain of f of x. And if we're looking for differentiability, we're looking at the domain of the derivative. All right, so we know that a function is increasing. So a function is increasing on the closed interval from a to b if f prime of x is greater than 0. So if f prime of x is greater than 0, then our function is increasing. And we know that our function is decreasing if f prime of x is less than 0. And then f is considered constant on that interval from a to b if f prime of x is equal to 0. So if we take a look at kind of that concept here, so I'm just going to draw a parabola shape. And we'll say this is our f of x. So if I take a look at that, I know that if I were to pick any point here on the right-hand side, so if I were to choose any point on the right-hand side, I would see that the slope of that tangent line is positive, right? So if the slope of that tangent line is positive, then that's saying the derivative is positive. And it doesn't matter where you are on this side right here, your slope will always be positive. And that we know on this side our function is increasing because as we go from left to right, it's going uphill. Whereas if I were to look at the other side of the parabola, so this side over here, and I were to draw, so I just randomly picked a point and drew a tangent line over here, I would see that the slope of this tangent line is negative. So if the slope of the tangent line is negative, then that means that our function is decreasing. And so again, on this half of the parabola, as I go from left to right, the function is going downhill, so it would be decreasing. Okay? And then we call a function monotonic if it is either, or strictly monotonic, excuse me, if it is either increasing or decreasing on the whole interval. So this would not be considered strictly monotonic because we are decreasing and then increasing. So monotonic would be like your cubic function, x cubed, for instance. Okay? All right, and then we have what we call the first derivative test. So the first derivative test we're going to be using to find relative maximums and relative minimums. So back in Math 3, Honors Math 3, of course, we did find maximums and minimums, relative maximums and minimums. And we didn't use a calculus definition for it. We just talked about a function that changes from like increasing to decreasing or vice versa. So we're going to add kind of that derivative component to decide, you know, the maximum and minimum. So we don't need calculus per se to find it visually because we have worked with that already, but we're still going to go over that. Okay, so if your derivative changes from negative to positive at c, then f of c is considered a relative minimum. Whereas if f prime changes from positive to negative at c, then f of c is a relative maximum. So just a few things to kind of make sure we're clarifying is that if you notice right here, they're specifically saying f of c is your relative maximum, relative minimum. And so just a reminder, this is your value of y. So oftentimes they'll ask, like, what is the relative maximum? Then make sure you're answering in terms of y. Okay, so answer in terms of y. If it says that what values of x is your relative maximum located, then you would answer in terms of x. Okay, so make sure in general if they're asking for what is your relative maximum or minimum, that you're answering in terms of y. So they're saying specifically here that when f prime changes from negative to positive. So when f prime is negative, that means your slope is negative. So if your slope is negative, then your function will be decreasing, right? Isn't that what that's saying? So if f prime goes from negative to positive, so you have a negative slope to a positive slope. So if you have a negative slope that switches to a positive slope, then you have to have a relative minimum somewhere, right? And that's what this is saying. So a negative sloped curve, well, this looks kind of absolute value, but a negative slope curve to a positive slope curve, then you will have a relative minimum, right? Isn't that what that's saying? Versus, if we take a look at number 2 here, where it says your f prime changes from positive to negative. So f prime is positive, so you have a positive slope, right? Positive slope section, so these would all be positive slopes here. And it switches to negative slopes, so positive sloped lines to negative. Then you would have a relative maximum, right? And so our definitions last year, the year before, depending on when you were in Honors Math 3, talked about if your function goes from decreasing to increasing or increasing to decreasing, that's how we decided if we have a relative min or max. And we're just adding in that derivative calculus component, okay? So here's like just another review idea just to kind of make sure that we're kind of on that same thought process of what do we know algebraically to what are we going to work with calculus. So this is just some random, function f of x, and what we're looking for are the open intervals, so we'll be using parentheses, for where f is increasing or decreasing. And I just noted that these do not have their values on them, so I will do that. So again, this is f of x. So this is from before, right? So our function is increasing when we would visually look and say, oh, we're going uphill. So we're going uphill along this line right here, right? So uphill along this line right here. So I would say that f is increasing. I'm going to abbreviate that, INC, on the open interval, so open interval meaning not including, from negative infinity to negative 1. So remember, this is the left x to the right x, so left to right. So from negative infinity to negative 1. And then it's increasing again on this little section right here as well. So increasing meaning going uphill. And so we use that union symbol, remember that? And then that is from 1 to positive infinity. So again, that's just visualizing, where is it increasing? So then it's decreasing whenever it's going downhill as we move from left to right. So f of x is decreasing. So that would be just this middle section right here. And that would be from negative 1 to positive 1. And then this, remember, is a relative maximum and a relative minimum because our graph goes from increasing to decreasing at negative 1 and then decreasing to increasing at positive 1. Okay, so that was using our definitions last year. All right, so let's take a look at when we would use calculus to figure all that information out. Okay, so we'll take a look at this first example. So we want to find the critical numbers, if there are any, and also the open intervals on which f is increasing and decreasing, and locate any of the relative extrema, right? Find the values of x, for that relative extrema. So we're going to do the steps just off to the side. So again, you may want to press pause here and there to copy down and get caught up. So the first thing we want to do is we want to find our critical numbers. So that was in our objective 1. So to do that, remember we take our derivative. So we have to find f prime of x. And when we do that, we want to equal that to 0. And also look to see if there's any place where it's undefined. Okay, and then I'm just going to do that. So we, in general, though, want to find the derivative, equal it to 0. And then if we happen to have a fraction, then we look for where it's also undefined, right? Look for where it's undefined. All right, so we're going to go ahead and take that derivative. So you should be pretty adept at that. So go ahead and take that derivative, press pause, and see if you can find your critical numbers on your own. So this derivative would be 6x squared plus 6x minus 12. And then I want to equal that to 0. There's no place where it's undefined. So when I equal it to 0, I'm going to go ahead and do a GCF so I can factor out that 6. And then factor that trinomial, so that would be x here, and then positive 2 and negative 1. So that would be that factor, and then now use zero product property, so I'm going to set each of these equal to 0. So that would be at negative 2 and positive 1. So there are my critical numbers. Okay. All right, and then once I do that, then the second thing that I'm going to do is I'm going to do a number line analysis. So we did this in first semester of Honors Math 3, or if you're in Calc AB, same as well, first semester. So we're going to do a number line analysis. For f prime and the critical numbers. So we're doing a number line sign analysis for f prime and the critical numbers. Okay, so then I'm going to go ahead and set up a number line here. Make sure you always label it f prime because we are going to be using sign analysis for f double prime as well. And then also, like in Math 3, we used it for just f of x. So we're going to do it for f prime. And so I'm going to put the critical numbers, so this is a number line here. So I'm going to put the critical numbers, making sure I'm smallest to largest, so negative 2 and 1. And so I don't need to mark the rest of the information, like I can mark like 0, 1, 2, 3, but I just need to make sure I have my critical numbers on there. So just a reminder for a sign analysis, so what you're doing is, so this is where the derivative is equal to 0, right? The derivative is equal to 0 at both of these values, right? Because that's what we did up here above. So the derivative is equal to 0. Now we need to figure out, okay, to the left of this place where it's 0, what is the sign, positive or negative? And then the same here, what is the sign of the values in between here, positive or negative, and then here, positive or negative. So I know this is where it's equal to 0, and the only way for this to be 0 is it has to transition, right? It has to transition from positive to negative, negative to positive. It's also possible for it to go positive and then just plateau and then go back positive again, right? Or negative, plateau, negative again. So how we do that sign analysis, so just a reminder, is you just pick any number in the interval and then you evaluate it into your factored form is usually the easiest. So I'm going to pick a number smaller than negative 2. So let's say I pick negative 3. And then I'm going to substitute that into here. So then that would be 6 and then negative 3 plus 2, negative 3 minus 1. So I just evaluated and replaced all the x's with negative 3. And then remember, I'm not really interested in what the numerical value is. I just want to know, is it a positive or a negative number? So I have 6, right, which is positive. And then I'm going to multiply that by negative 3 plus 2, which is negative, right? And then negative 3 minus 1, which is also negative. So the product of a positive and two negatives is positive. So that means that no matter what I choose over here, right, whether you pick negative 4, negative 5, negative 6, it doesn't matter. When you substitute it into here, you're going to get a positive number. So again, I don't care that this is positive 6, I just care that it's positive. I don't care that this is negative 1, I just care that it's negative. And I don't care that that's negative 4, I just care that it's negative. Okay? And then I'm going to do the same thing for the middle interval, so f prime, so pick a number between negative 2 and 1. I'm going to pick 0. And then I'm going to do the same thing again. So I have 6. And then I'm going to replace x with a 0. And again over here. And then I'm going to decide what is that sign going to end up being. You know, is it positive or negative? And so that would be 6, which is a positive number, times 0 plus 2, which is a positive number, times 0 minus 1, which is a negative number. So then that product here would result in a negative. So I know anything I choose between -2 and 1 would be negative. And then finally for the last one here, so f prime, pick a number bigger than 1, so say 2. So this time I'm not going to actually substitute it in, I'm just going to put my signs down. So I have 6, which is positive. Replace x with 2, so 2 plus 2, so that would be positive. And replace x with 2 here, so 2 minus 1, so that would also be positive. And so the product of 3 positives would be positive. Okay. So there's my number line sign analysis. And then now I'm going to use the definition to make my conclusion, right, or to answer the question. So now use the definitions. So DFN definition. So use my definitions to answer the question. All right, so what are those definitions again? So wherever f prime is greater than 0, f is increasing, right? Wherever f prime is less than 0, f is decreasing, right? That was part of that definition. So I know f prime is greater than 0 here and here, right? So then my conclusion, so I'm going to have to kind of squeeze it in here. I'm kind of tight on space, so I'm going to make it fit right there. So I know f is increasing on the interval, so on this section right here, so -infinity to -2. And then also in this section here, so that would be from 1 to infinity. And then I also know that f is decreasing when f prime is less than 0. So that would be just in that section there. So f is decreasing on the interval from -2 to 1. And then finally, it also asks for your relative extrema, so relative max and min. So we have a relative max when x goes from increasing to decreasing, right? So when f goes from increasing to decreasing. So that would be when f prime goes from positive to negative. So f prime goes from positive to negative at -2. So then there would be a relative max at x equals -2. And then finally, a relative minimum. So a minimum is when we go from decreasing to increasing. So we were decreasing, right? We were decreasing on this section, or f was decreasing, right? So f was decreasing here because f prime was negative. And then it switched to increasing right here. So f switched to increasing here because f prime was positive. So then we have a relative minimum at x equals 1. Okay? All right. So let's do one more example similar to that. This one's a little tougher derivative, so this one will challenge you just on the solving component. So you might want to press pause and try to do the derivative here, and the derivative not so challenging, but maybe the solving might give you a little trouble. Okay, but go ahead and press pause, try that one. All right, so if I go to do this derivative, I want to make sure I'm using product rule. So that would be equation 1 and equation 2, right? So I would use product rule for this. All right, I'm just going to do it off to the side here. So then f prime, so I'm going to do 1d2. The derivative of x minus 5 would be 1x to the 0, which is just 1. So 1d2, and then plus 2. And then d1, so just power rule here, so that would be times 2/3 and then x to the -1/3. And so I do know I have to solve this, so lots of different ways to solve it. So I'm going to do it just by just kind of doing a rewrite. You might want to factor it. If you're really good at factoring, I would just do a GCF and factor that. If you're a little like, factoring's not your strength, maybe then do a rewrite and try to go that route. Okay, so I'm going to do the rewrite. But again, if you're good at factoring, that's what I would suggest doing, is the factoring side of it. So take that and do a little rewrite, so and equal it to 0. So I would have x to the 2/3, and then I'm going to have plus, and then 2x minus 5, and then I'm going to put the 3 and the x to the 1/3 in the denominator. So the 3 in the denominator, because it is the denominator, and then this has a negative exponent. All right, and so then from here, I'm going to go ahead and subtract this to the other side, okay, if you want to, like lots of different ways, or clear your fractions by multiplying. So different ways to kind of attack this. I'm going to clear my fractions, and I'm going to multiply. So I'm going to multiply both sides by 3x to the 1/3, and that's just to get rid of that fraction. And so it'll distribute to both of these, and then to the 0 as well. So when I multiply these together, I'm going to add my powers. So I have 2/3 plus 1/3, which is 3/3. So that would give me 3x to the 3/3, which is just 1. And then plus, when I multiply these together, the 3x to the thirds will cancel, and so that's just going to equal 1, right? So right here, this will just equal 1. So then I just have left the 2 times x minus 5. And then equal 0 times that will just be 0. So then I'm going to go ahead and distribute and then combine like terms. And so I will have 5x minus 10 equals 0. So 5x equals 10, and so x is equal to 2. Okay. So the first thing, right, is we find our critical number. So I set the derivative equal to 0, and then I found that critical number. And then also remember that our critical numbers are where it's undefined, so at the excluded values of the derivative. So this was my derivative right here, right? And so do I have any excluded values? Then I will, right? I'll have an excluded value here because I have a denominator. So then my critical numbers are at x equals 2, but also I have a critical number at x equals 0. And again, because that is an excluded value of the derivative. And it is also in the domain of the function, right? So can x equal 0 here? Yes. Okay, so then I actually have 2 critical numbers where the derivative is equal to 0, and also when it is undefined at x equals 0. So I have 2 critical numbers here. Okay, so then once I get my critical numbers, I want to do a sign analysis. So I'm going to substitute in 0 and 2 onto my number line, making sure I label it. And then I want to pick numbers in each of these intervals and substitute it into the function and see if I get a positive or a negative number. So again, you can pick any numbers, it doesn't matter, and you're going to substitute it into the derivative. I'm going to choose to put it into this form of the derivative right here because that's pretty darn easy, yeah? That's some easy arithmetic going on there. So my f prime simplified to 5x minus 10, right, when it was all said and done. So I'm going to go ahead and use that to do my sign analysis. So 5x minus 10 will be where I do my analysis. So if I substituted -1, I would get -5 minus 10, which is negative. If I substitute in +1, hold the phone here. Wait, did I do that right? So -1. I think I have a mistake here somewhere. Hold on. Let me think. What am I doing wrong? So if I put in -1, so I think, oh, yeah. Okay, sorry. Undo that. Okay. I need to be looking up here when I'm putting in my derivative, because this is my derivative pre-simplified, right? I don't want to do the modified form. So let me scooch that little bad boy over here. Okay. All right. So all of a sudden I'm like, wait, hold on. I was about ready to make a mistake. There we go. So let's put that -1 in. Okay, so -1. So when I square it, that turns positive, and then cube root positive. So that would be 1. And then -1 minus 5 is -6, and then that would be -12 over 3, which is -4. And so then that would give me still a negative value. Okay, but we're playing it safe there. All right, and then now I want to go ahead and evaluate this at +1, so a number between 0 and 2. And so let's see, I would get, doing some mental math here, so 1 plus -8 over 3. So 1 minus 8/3. So that would be 0. 1 minus 8/3, so that would be negative. And then let's go ahead and evaluate it at a number bigger than 2, so say 3. So that would be cube root of 3 squared. Okay, let me not do 3. Let's do 8, because I can take the cube root of 8. So I don't have a calculator. If I had a calculator, this would be so much easier. Okay, so the cube root of 8 is 2, squared is 4, so that would be 4. I need to do some numbers here. 8 minus 5 is 3, times 2 is 6. Over the cube root of 8 is 2, so 6, 4, 1, positive. So positive, there we go. Okay, so then I have a critical number, or excuse me, then I have those values there. Okay, and then I should get a calculator to check my other arithmetic here, but we're hoping I'm right. If I made a mistake, I apologize. Okay, that's the hazard of mental math, Okay, so then I am going to analyze this. So then I have where f is increasing, wherever f prime is positive, so that would be on this section here. So that would be on the open interval from 2 to infinity. Okay, so f is increasing on the interval from 2 to infinity. And then we have f is decreasing whenever f prime is negative, and so that would be on these two sections here. And it's undefined here, so I want to make sure that I'm going to say from negative infinity to 0, and then again from 0 to 2. And then we also want our, so this was our critical numbers. Let me label that up here, critical numbers. All right, and then we have our relative max and min. So f has a relative max whenever x goes from positive to negative, right? So increasing to decreasing, and that's nowhere, right? Because it's decreasing because of the negative slope, decreasing, and then increasing. So there would be none. And then finally we have a relative minimum whenever f goes from decreasing to increasing, which is when f prime goes from negative to positive, and that occurred at x equals 2. Okay, so there is that. And then finally our last little spiel, okay, so our last little spiel right here. Okay, so our summary. So this is kind of what we'll be using to help us out with the last example here. So for example 2, so this is just a summary, our definitions using calculus, right? So f has a critical number when your derivative is either 0 or undefined. F is increasing if your derivative is positive. F is decreasing if your derivative is negative. F has a relative maximum if f prime goes from positive to negative. And f has a relative minimum if f prime goes from negative to positive. So you really need to know these definitions. I would highly suggest you make flashcards or do something to really make those stick in your brain. Okay, so super important that those stick in your brain. Okay, so with that said, let's go ahead and take a look at this last bit. So this is saying, given the graph of f prime, right? So that means this is f prime right here. You want to find the critical numbers of f and the open intervals in which f is increasing or decreasing, and find the values of x for all the relativeixorema for f of x. So the most important piece here that you need to make sure you're paying attention to is that you are given f prime, but you are being asked questions about f. So that means you cannot say, oh, there's a relative minimum for f, because this is not a picture of f prime. I mean, this is not a picture of f, right? It's a picture of f prime. So you cannot just look like you did in Math 3 and say there's a minimum, there's a max, there's increasing, there's decreasing. You have to use your definitions. So I would just do it a piece at a time. So if we want to find the critical numbers for f, then we need to go to the definition. And so the definition says that if you're going to look for a critical number for f, right? So the critical number for f, then you have to know where f prime is either 0 or undefined. So when I say that f prime is 0, then that's what you need to be focused on. So you're not looking for critical numbers, right? You're looking for where f prime is 0. And that result will give you the critical numbers. So you have to kind of read that definition backwards. So I know that f prime is equal to 0 at x-intercepts, right? That's occurring at x-intercepts. So if I look at this picture here, where do I have x-intercepts? So I have one here and here. So then I would say, all right, I have an x-intercept. Oops, I don't want to write in red pen there. I have an x-intercept at x equals 1 and 4. So what is that telling me? So then that is telling me that f prime is equal to 0 at x equals 1 and 4. Right? Like that needs to be my train of thought. So then if that is where f prime is equal to 0, then that is also where f has a critical number. So then that means, so both of these conclude that, like this thought process then is that f has critical numbers at x equals 1 and 4, right? So you're reading that kind of definition a little bit backwards. Okay, so making sure you're always kind of tracking those thoughts. Okay, so once again, so f has a critical number whenever f prime is 0 or undefined. So this is a picture of f prime. So it's 0 here. So because it's 0 here, then f of x has a critical number there. All right, so the second thing we have to do is come up with the open intervals for where your function is increasing or decreasing. So I know f is increasing, right? So I'm going to go to that definition here. So f is increasing when f prime is positive, meaning f prime greater than 0. So well, greater than 0 means above the x-axis, right? Above the x-axis. So I want to not fixate on where is f increasing. I want to fixate on where is f prime positive, because this is a picture of f prime. So f prime is positive when it is above the x-axis, so that would be here and here. So if that's where f prime is positive, right, so f prime is positive here and here, then f is increasing. So f is increasing where f prime is positive, so that would be negative infinity to 1, and then again from 4 to infinity. All right, so what about f decreasing then? So f decreasing is when f prime is negative. F prime is negative when it is below the x-axis. So where is it below the x-axis? That would be this section right here. So f prime is below the x-axis, negative here. And when f prime is negative, then our function is decreasing. So then I would say that f is decreasing on the open interval from 1 to 4. All right, so now relative max and min. So we know that f has a relative max. And we're also looking for that relative min. So the definition, so again, we don't look at the picture for relative max and min, we look at the definition, right? So we know that we have a relative maximum when f prime goes from positive to negative. So f prime has to go from positive to negative. So if I look at this picture, f prime has to go from positive to negative, and that happened here. So at x equals 1, I'm going to have a relative maximum for f of x. Not f prime, but for f of x. So where does f prime go from positive to negative? At x equals 1. So therefore, f will have a relative maximum there. And then we know we have a relative minimum when f prime goes from negative to positive. So I look over here. Where does f prime go from negative to positive? That happens here. So f prime goes from negative to positive here. So therefore, x equals 4 will give me my relative minimum. So again, those definitions are very important for us to analyze our graphs. All right, so let's take a look at B. So you may want to press pause and try this one on your own. Okay, so let's start with our critical numbers. So I think about critical numbers, I think about the definition. So I know that f has critical numbers when f prime is equal to 0. So it's equal to 0 here, here, and here. So that would be at negative 1, 2, and 4. Where is f increasing? F is increasing whenever f prime is positive. So I'm looking at the definition. So where is f prime positive? When it's above the x-axis, so that would be here. So from negative 1 to 2, and then again here, and that would be from 4 to infinity. whereas f is decreasing wherever the graph of f prime is negative, so below the x-axis, so that would be here and here. And so that would be from negative infinity to negative 1, and then again from 2 to 4. And then for our relative max and min, so the definition of a relative max is when f prime goes from positive to negative. So it was negative here, positive, negative, positive, right? So when we have a relative max when f prime goes from positive to negative, so that occurred at x equals 2, and then nowhere else. And then finally, our relative min is when f prime goes from negative to positive. So f prime goes from negative to positive here, so at x equals 1, and here at x equals 4. Okay, and that's it.